This is a Bosch Rexroth EFC5610 inverter drive, and this is a ctrlX Core X3. In this video, I'm going to show you how to build a brand new PLC program completely from scratch to control the EFC5610 over EtherCAT. Hello, I'm Simon from the Inverter Drive Supermarket. In the previous videos, I walked you through setting up EtherCAT communication between a ctrlX Core X3 and an EFC5610 drive. Now we're ready to move on to the next step, building the PLC program. To follow along, you'll need a Bosch Rexroth EFC5610 with multi-Ethernet option card installed and configured. We're using one of the smaller ratings here, but the same process applies all the way up to 160 kilowatts and beyond. You'll also need a ctrlX Core X3 with both the EtherCAT master and PLC apps installed and licensed. All of these setup steps were covered in the previous video, so if you missed those, check the links in the description. Alright, let's get started building the PLC program. The software package we need for this is ctrlX PLC Engineering. You can download it for free from the Bosch Rexroth website. Visit community.boschrexroth.com and click ctrlX Automation, then Download. Select your location if prompted, and log in. If you haven't registered yet, take a moment to create an account first. Once logged in, search for ctrlX PLC Engineering. Then select the folder in the results. The Core X3 I'm using is running firmware version 2.6, so that's the version I'll select. Then simply download, extract, and install the latest version. Once PLC Engineering is installed, open it. Click New Project. The New Project dialog appears. Ensure the project's category is highlighted and select the correct project template for your core. The x64 template is for the Intel Atom-based X5 and X7. We're using an X3, so we need the ARM64 template. Give your project a name. I'm going to call mine Demo PLC Project, and click OK. The new project will take a few moments to initialize. In the previous video, we set up EtherCAT communication for real-time data between the X3 and the EFC5610. Now we need to connect to the X3 so we can read this data. Double-click Device to bring up the Communication tab and enter 192.168.1.1 into ctrlX OS Device and press Enter. Enter your usual X3 credentials when prompted and click OK. Install or accept the certificate, and we're connected. Now we'll select what real-time data we want to work with. Right-click Data Layer Real-Time, select Real-Time Data, then selectively from ctrlX Core. In the Select a Real-Time node drop-down, select EtherCAT Master Instances EtherCAT Master, and expand XFCO1 Rexroth mode. The process data objects, or PDOs, are shown from the point of view of the EFC5610. It can receive RX, a control word, and transmit TX, a status word. Select both. It can also receive a frequency command and transmit its current frequency setting in real time, so we'll select those too. The XB EC12 node is the bus coupler I have in our demo rig. We don't need it for this project, so can leave it unchecked. Apply the selections using the button in the middle. Then expand the EtherCAT master node on the left to confirm they've been applied to our PLC project. They have. Perfect. Now we have what we need. Click Close. We'll be adding a few project files, so it makes sense to keep them all in the same folder. Right-click Application, select Add Folder, name it EFC, and press Enter. Right-click on the EFC folder, select Add Object, and POU, Programmable Organization Unit. Name it PRG EFC01. Confirm that the type is Program, and select Ladder Logic Diagram LD as the implementation language. Click Add. Now we have two programs, so I'm just going to call PRG EFC01 from PLC_PRG. Double-click PLC_PRG to open it, then right-click the lower window and select Input Assistant. Ensure POU/Program and Function Calls is selected in the left window and expand Application and the EFC folder. Double-click PRG EFC01, it appears in the bottom window. Now the old program will call the new one. A struct, short for structure, is a bit like a container for variables that logically belong together. As the control word contains a number of variables, a struct seems a perfect fit for this. So right-click EFC, select Add Object and select DUT, Data Unit Type. Name it UDT_EFC control word and click Add. The UDT prefix means user-defined type, so let's define it. Paste the following into the struct. It's the definitions for the control word from the manual. We'll follow the same process for the status word. Right-click EFC and select Add Object and DUT. Name it UDT_EFC status word. Check it is of type structure, click Add and paste the following. Now the structures have been created, we need to define them as variables so we can use them to hold data. Select the PRG EFC01 tab and add the following variables. First, add ST control word for the control word struct. Then add ST status word for the status word struct. But these structures and variables simply define something. Now we need to specify what. The status word is a 16-bit value transmitted over EtherCAT by the slave, the EFC, to the master, the X3. The first 8 bits indicate states such as running, accelerating, error, and so on. We need to extract these values and convert them to the struct we created earlier so that they're simple to work with. Right-click in the upper part of the bottom window. This is the first rung of our ladder program. Then select Insert Empty Box with EN/ENO, meaning with Enable Output. A box or function block receives an input, performs some kind of internal logic and produces an output. Fortunately, Bosch Rexroth provide a function block to convert a 16-bit word like the status word to a series of Boolean true-false values. To convert our empty function block, click on the question marks inside the box, then on the ellipsis button that appears. In the Input Assistant dialog, ensure the Text Search tab is selected and search for IL_word. Select CXA Utilities IL Word to Bool in the results. The CXA Utilities prefix means ctrlX Automation Utilities, so we know this is part of the Bosch Rexroth SDK and not a generic Codesys or IEC library. The IL prefix means inline, a simple stateless utility block that executes immediately, and Word to Bool is what it does. So double-click to select it, then click anywhere on the rung to update the function block. Click again to open the Auto-Declare dialog, then simply click OK. There's nothing more we need to set. We don't need the contact on the enable so we can select and delete it. This just means the function block will always be enabled. Double-click on the input and change it to W status word. The W prefix indicates a 16-bit word type and it is the status word. The Auto-Declare dialog appears. Check that the type is word. It is, that's good. Click OK. Now we can assign each of the output bits to variables from the status word struct we created earlier. Click on the question marks next to bit 0, then on the ellipsis button that appears. Ensure the Categories tab is selected, expand the ST status word variable in the panel on the top right, select bbit0 reverse and click OK. Do the same for bit 1 and select bbit1 running, and again for bit 2 and select bbit2 jogging. Repeat the process for bits 3 to 7. The question marks for the remaining bits can be deleted as they represent the error code and need to be handled separately. We'll do this next. The status word transmitted by the slave also includes the last error code. This can be found in bits 8 to 15 and is a numeric value. As 8 bits equal 1 byte, the field within the struct we created for this was a byte and not multiple bits. Right-click on the rung and select Insert Empty Box with EN/ENO. Click on the question marks inside, then the ellipsis button. In the Input Assistant dialog, ensure Text Search is selected and search for IL_highbyte. Select it in the results. The IL_highbyte function extracts the high byte from a 16-bit value, so bits 8 to 15, exactly what we need. Double-click, then click away. The input should be the W status word variable as before. and the output should be assigned to the ST status word by bit 8 to 15 error code variable. So now we can read the status word and convert it to a series of variables in real time. Let's do the same for the setting frequency. The setting frequency is also 16-bit, but it represents a scaled numerical value corresponding to parameter D0.02 in the EFC. So we need to add a function block to convert this 16-bit value to a number so it's simple to work with. Add a new rung to the ladder, then insert an empty box with ENO. Delete the contact on the enable, and name the function block word_to_real. Enter wSettingFreq as the variable name for the input. Then in the auto declare dialog, set the type to word and the initialization value to 0. Enter rSettingFreq as the variable name for the output. Set the type to real and the initialization value to 0.0. The frequency reference resolution is 0.01 Hz, so we need to divide the EFC value by 100 to get the value in Hertz. Insert a second empty box with ENO. Click on the question marks, then the ellipses, change to the text search tab and enter div. Select div in the results, and click away to update the function block. The two inputs will be divided to become the output, so assign one to the rSettingFreq variable and set the other to 100. The output can be assigned to rSettingFreq2 as another variable isn't necessary. That's the status word and setting frequency sorted. Let's move on to the control word and frequency command. The control word is a 16-bit value transmitted by the X3 to the EFC. It tells the EFC what to do, like run, stop, or reset fault. To use this to control the EFC, we need to convert the series of true-false values in our control word struct into a 16-bit value which the EFC will understand. Add a new rung to the ladder. Then add an empty function block with enable output. The Bosch Rexroth SDK also includes a function which can convert a series of Boolean values to a 16-bit word, which is just what we need. Open Input Assistant, select the text search tab and search for IL_bool. Select IL_bool to word in the results. Again, we don't need the contact on the enable, so can delete it. Click on the output side and name the new variable wControlWord. Check that the type is word and click OK. Now we can go through each of the bits on the input side, assigning them to the control word struct properties. We'll start with bit 0, the run command. Then bit 1, the jog command. Bit 2, the reverse command. And so on. For reserved bits 9 to 15, we can set them to 0 since they won't be used but are required by the control word. The final step is to add a rung to process the frequency command. It will come as no surprise that the frequency command is a 16-bit value. Like the setting frequency, it represents a scaled numerical value and is used to set the desired frequency. So we need to add a function block to convert our numerical frequency command value to a correctly scaled 16-bit value for the EFC. Add a new rung to the ladder and insert an empty function block with enable output. Name the function real_to_word and delete the contact on the enable. Click on the output side and name the new variable wFreq command. In auto declare, set the type to word and initialization to 0. On the input side, name the new variable rFreq command. In auto declare, set the type to real and initialization to 0.0. This ensures that the rFreq command variable is set up correctly. On the input, change rFreq command to rFreq command multiplied by 100 to correct the resolution to 0.01 and suit the drive. I've added real to define 100 as a real literal rather than any other data type. That's the ladder complete. Before we move on to the visualization, we need to map each of the word type variables to the real-time data the PLC will exchange with the EFC. To do this, first double-click on the XFC01 Rexroth mode node in Data Layer Real-Time. You can see the real-time data channels we scanned for and added earlier. However, there are no variables assigned to any of them. This means that the input and output variables in our PLC program are effectively disconnected from the EFC. To fix this, we need to map each channel to a variable. Double-click the variable for status word and click the ellipsis button. Expand Application, EFC, and PRG EFC01 to see the PLC program variables. Select W status word and click OK. Repeat the process for the remaining 3 channels. They are setting frequency, which should be mapped to W setting freq, control word, which should be mapped to W control word, and frequency command, which should be mapped to W freq command. Now the variables are mapped, we have everything in place to both control and read the status of the EFC in real time. At this point, there are a multitude of possibilities for this PLC program. The fact that you're watching this video probably means you have something already in mind for your setup. So to demonstrate that everything is working properly, I'm going to use a visualization. Right-click on the EFC folder, select Add Object, then Visualization. Click Add. Let's first add a rectangle as a header. You'll find these in the toolbox on the right in the Basic group. I'll drag it into position, then set the text property to Command, as this will be a column of buttons to control the EFC. Once the header is in place, I can add the first button. Buttons are in the Common Controls group. Each button will represent a control word bit. So I'll set the text of the first button to 0 Run command. Next, I need to bind the button to the correct variable. There are 2 options: toggle, which behaves like a switch, and tap, which behaves like a momentary push button. I only need a momentary signal for the run command, so tap is the correct option here. Using Input Assistant, I can expand the ST control word variable and bind the button to bit 0, the run command. And that's the first button done. Next, I'll add a button for jog. The jog command should only be active whilst the button is pressed, so tap is the right choice again. Using Input Assistant, it's easy to find bit 1, the jog command, and bind it to the button. The next button we need is reverse. The reverse command is slightly different as it only sets the direction of rotation, it doesn't start or stop the motor. In this case, toggle is the appropriate option. Again, we can use Input Assistant to bind the variable to bit 2, the reverse command. Now you can see how this works, I'll add the remaining buttons. Bit 3 is stop according to the EFC parameters. Bit 4 is emergency stop. Bit 5 is fault reset. Bit 6 is stop accelerating or decelerating. Bit 7 is the control word active command. It's the most important bit because if it's false, all other control word bits are ignored. The control word active binding should be a toggle type and can be bound to bit 7 using Input Assistant. I'm not going to add a button for bit 8, coaster stop, for this example. Now that the control column is complete, I can add a header for status. Again, I'm using a rectangle for this. I'm actually going to use rectangles for all the status bits as the background colour can indicate the state. The first status bit is bit 0, reverse. I'm going to bind it by colour and set it to ST status word bit 0 using Input Assistant. Colour bindings have 2 states, normal when the variable is false and alarm when it's true. Since reverse is not an alarm condition, I'll change the border colour to black and the fill to light green. The next status bit is bit 1, running. Again, this isn't an alarm, so I'll set the border colour to black and the fill to light green. I can use Input Assistant to bind the colour variable to bit 1. Next is bit 2, jogging. This isn't an alarm either, so I'll set the border to black and the fill to light green. Then I can use Input Assistant just as before to bind the colour variable to ST status word bit 2. The same process applies to status bits 3 and 4 for accelerating and decelerating. Status bit 5 is stall over voltage, and this one is different because it is treated as an alarm. So here I only need to change the border to black. The default pink fill colour is fine for an alarm state. I can set the colour variable to bit 5 using Input Assistant as before. Repeat the process for bit 6, stall over current, and bit 7, error. Next to the error indicator, I've added another rectangle to display the last error code. In this case, I'll use the text property to show the code. To do that, I simply add %s as a placeholder with the s suffix specifying that the value should be treated as a string. Now we can add a potentiometer to set the frequency command. You can find this in the toolbox in the measurement controls group. Once it's in position, bind the variable to rfreq command using Input Assistant. I'm also going to make a few changes to the scale. The main scale will be more useful set to 10 instead of 20. And since I plan to run the EFC up to 50 Hz, it makes sense to set the scale end to 50. Finally, I'll add a label so it's clear what the potentiometer is for. Labels are in the Common Controls group. Just drag one into place and set the text property as required, in this case, frequency command. And that's the potentiometer done. The last part of the visualization is a meter to display the setting frequency. This can also be found in the measurement controls group. Once it's in place, bind the variable to rSettingFreq using Input Assistant. I'll also change the scale to match the potentiometer. Set the main scale to 10 and the scale end to 50. Again, I'll add and position a label. For this video, the text will be setting frequency. In the next video, I'm going to make some improvements so the label will change. And that's the visualization complete for now. Now that the program is complete, it needs to be transferred to the X3 so we can run it. To do this, select Online and log in from the menu. Click Yes to proceed with the download. Once the application has been transferred, both the device and application will be highlighted in green. However, you'll notice that the application is currently stopped. To run it, right-click Application and select Start. The application status changes to Run, and we're ready to try it out. As usual, we're using our EFC5610 and ctrlX X3 demo rigs to try this out. First, we click the Control Word Active button. This toggles bit 7 and tells the EFC to expect a command. Then we click the Run command button, that's bit 0, and this momentary signal instructs the EFC to run the motor. Finally, we set the speed in Hertz using the potentiometer and the motor starts running. If we click the Reverse button, bit 2 is toggled. The motor slows to a stop and then accelerates to the same speed in the opposite direction. Toggling bit 2 again repeats the process. We can press and hold the Stop Accelerating Decelerating button to hold the current motor speed. Releasing it allows the EFC to continue accelerating or decelerating. Pressing the Stop Parameter button, bit 3, sends a momentary signal telling the EFC to stop the motor according to current parameter settings, in this case, ramp to stop. We can also press and hold the Jog button to set bit 1, which, as the name suggests, jogs the motor. But there's one issue I'm not happy with and I think could be improved. If I run the motor again, you'll notice the setting frequency shown on the meter changes with the potentiometer. The problem is that this value is simply a reflection of the frequency command. It doesn't show the actual output frequency of the motor. Unfortunately, output frequency isn't included in the standard device profile, so we'll need to add it. We'll do that in the next video. Thanks for watching. I hope you found this video helpful. If you did, please give it a thumbs up and consider subscribing. We really appreciate your support. See you next time. This video is for educational purposes only. Always follow official manufacturer documentation and safety instructions.